Hello everyone, today in this video we'll look through the sample problem and try to solve it using the Python code. So before writing our code, let's just look at our question and determine what we need to do in order to solve this question. So we're given this question right here. So an open container initially at 1 atmosphere and 298 Kelvin contains 1 kilogram of liquid water. The container is sealed without removing the air, then heated to a pressure of 2 bars, at which the vapor space contained 0.3 moles of water. What is the final temperature? What is the total volume of the container? Explain your solution approach on a whiteboard or a suitable alternative before writing your Python code to solve the problem numerically. So we'll just start by drawing what's happening. So we have our container, and so we'll have our liquid phase and vapor phase. And so let's just look at our question and determine what we need to find. So we're asked to find the final temperature and the total volume of the container. So we'll just say temperature final is equal, like we need to find temperature final and we need to find the volume total. And now let's look at what we are given. So we're given the initial pressure, the initial temperature, and the initial mass of liquid water. So we'll just say pressure initial would equal 1 atmosphere. So we need our units to be in SI units. So we'll just say 101,325 pascals, which equals 1 atmosphere. And we have our temperature initial to be equal to 298 kelvins. And the mass total would be equal mass of the water total equals 1 kilograms. And we're also given that without so the pressure would be 2 bars at the end. So we have our pressure final 2 bars, which is 200,000 pascals. And we have here the vapor space contained is 0.3 moles of water. So we have N vapor of water. We have N water in a vapor phase to be equal 0.3 moles. So as we are asked to find our total volume, let's just start by writing the equations we might know. So we know that total volume would equal the volume in liquid phase right here plus the volume in vapor phase, right? So then we also know that these 0.3 moles would equal the mass of water in vapor phase divided by 18 multiplied by 10 raised to the power minus 3 kilograms per mole, as we need it in a SI unit. And so we also have our second equation. So the mass of water total would be equal to the mass of water in liquid phase plus the mass of water in vapor phase. And the next thing we also know is, so the mass of the water total. So the mass of the water total is given in the question. So we have this, and the mass of the water in vapor phase. So we can find it as, we know that we have this equation right here, right? So we know that the moles of vapor phase of water in vapor phase would equal 0.3 moles. So then the mass of water in vapor phase would equal to the amount of water in vapor phase multiplied by 18 multiplied raised to the power 3. So then we also know that pressure total would equal to the partial pressure of the air and the partial pressure of the water, right? So as we know that air is a gas, we might assume it to be an ideal gas because we don't know what kind of gas it is, so we'll just use P air would equal, so it would be N air and R T, so our temperature would be the final, and we'll divide it by V vapor as it's in the vapor state. And so this is the pressure of the air, and we also might find the pressure of the water. So to determine that, we will use the Antoine equation. So this value is determined using the Antoine equation. So we have 10 raised to the power A minus B over C plus T, right? So now, to find the volume of liquid phase, we might use the equation. So we know that the density of the water in liquid phase would equal the mass of water in liquid phase over volume of the water in liquid phase, right? And then we also know that the remaining liquids is only consists of water. So we just use the water liquid phase, and we can say that the volume of the liquid phase to be equal to the mass of water in total minus mass of water in vapor phase, which is determined using this equation, over the density of the water in the liquid phase, in the liquid state. So we know our total mass, and we also know the value for the water in vapor phase, which we obtained using this equation. So another thing we also know is in order to find the pressure of the air, we need to find the moles of the air. So we also need the equation using moles of the air, amount of the air. So we also know that it is an ideal gas, so we might replace to be pressure of the air initially and multiplied by the volume of the vapor phase, vapor state, and that is divided by the R and temperature in initial phase. And from that, we know that the pressure of the air would equal to the pressure initial minus pressure of water initial. And for the water volume of the vapor, we can say that it equals volume total minus, so we know that the water of the liquid equals this equation, but when it was in initial stage, we didn't have any water in vapor state, so it would just be mass of the water total over density of the water over R temperature initial, right? So we have our next equation. And also, we might use another equation using amount of the water in vapor phase. So we know that amount of the water at vapor phase would equal to 0.3 moles. And so as we know that it would also be an ideal gas, we can say that it would equal the partial pressure of the water in final temperature multiplied by the volume of vapor divided by R and temperature final. So we have our next equation. So now, as we have all our required equations, we can solve for V total, and we can use these two equations and our Python code to obtain the value using the root solve function. So to solve our question using Python code, we will need to use our equation that we determined from the concept and apply it to the SciPy optimized root solvers to get the values for the total, for the final temperature and the total volume. So first of all, when we look at our equations here, we can see that we have our partial pressure of the water that is related to the temperature and the Anton equation. We also have the density of the water that is also dependent to the temperature. So to find the values for that, we'll go to our GitHub website, and when we go there, we can find the CHE tools. So that is a tool that could determine the values for the major properties of a substance using the temperature value. So if we go there and copy it, we would want to paste import it to our collaboratory, right? So we'd use exclamation mark get clone, and we'll paste our link. So if you try to run, clone, oh, so this was get sorry. So it has copied our SHE tools to the content and SHE tools. So what we want to do is to import that. So we would use import sys. So we'd use our shell. That would be sys dot pass dot insert. So we define our path. So that would be the first document on the content, which is CG tools, right? We'll just run it. So then, as we are working with the CHE tools, we should import that here, as we could import that at tools.gsg, right? I'll just leave it right like that. And I said like we will be working with the root solver from SciPy optimize, so it will be SciPy optimize root. So we will need to use this function to find the values, the final values that we're looking for. So we need to import that from SciPy optimize import root, right? So then when we look at our equations, we have one constant that is used probably everywhere, which is R. So as we are using the SI based units, we would use the value 8.134 to R. So we run it. So tools, content, tools. So we are missing S here, so that's why we're having an error message. So we run it. Then, so the SHE tools would determine many properties for a specific substance. So we would only need the properties for the water for this question. So it would be props, and inside of the brackets we would have the value water. So we would get all the properties for the water. So it's saying the warning message because the CHE tools is designed to work with the GPU, but we are running it with the CPU, so that's completely okay. Then, so when we go to the SciPy optimized route, we can see that we have to use function inside of the brackets when we're using the root. So first we will need to define our function that would solve for our temperature final and volume total. So we define equations. So it would get some vector, right? So we can unpack our vector. So it would be temperature final and V total and vector. And then we want our function to return here. If I add a code here, we know that the final pressure um, of the system should be 2 bars, and we know that the final amount of the water in vapor state must be 0.3 moles, right? So we can say that we want our pressure final desired to be 2 raised to the power 5, right? And we want our amount of the water in vapor phase, which is desired, to be 0.3. So here in the our function, we can solve for the P final and amount of the water in vapor state, and so that when we subtract the desired and the calculated values, we should get 0. Okay, we said final desired, and the same thing with when the vapor subtracted by vapor desired. So we run it. So here now we can include other nodes from the question. So we also know the pressure initial, which is 101,225 pascals, right? And then we know the initial temperature, which is equal to 298 kelvins. And we know that the total mass of the water total would equal to 1 kilograms. And we can also convert our values to float so that it won't be any errors when we are there won't be any errors while calculations. And when we like use the root solver here and put our equation, we would definitely want some initial values. So it would be our initial guesses. And one thing about our initial guess is that it really depends to the value we got actually. So if our guesses are too far from the original answer, we're gonna get an error message. So we might rerun the root solver several times until we solve the real equation. So this is why our guesses matter here. Okay, so let's just write the equations we know that can be related to the pressure final and the amount of the water in vapor phase. So one of the like one of the equations we know is that partial pressure of water depends on the Antoine equation, right? But as we're using the SHE tools determines the partial pressure of the water not using the Antoine equation, but something more advanced. So we use our SHE tools. So it would be PVAP in the final temperature. Okay, so we can have our next equation. So when we go here, we can see that N air, so the amount of the air would depend on this equation. So we can just write it here. So N of the air would be, so initial pressure subtracted partial pressure of water, which we determined from SHE tools. PVAP, but at initial temperature. So that thing matters here. Then we would subtract the volume total, subtracted the mass of the water total, right? Divided by the density of the water, which we can find using our SHE tools. In temperature initial, right? And that thing, everything would be divided by R multiplied by temperature initial, right? So we got our next equation. So then we also now know that the volume of the liquid is equal to the subtraction. So we subtract the volume of the vapor from the total volume. And we also know that the volume of the vapor, let's just not use that. So we can solve for a volume of the liquid first. Okay, let's use this equation now. So we know that the volume of the liquid is dependent to the density of the water in liquid state and the mass of the water in liquid state. So we'd have water volume of the liquid equal to the mass of the water in liquid state, right? Liquid state divided by the density of the water in liquid state, which is determined by the CHE tools, right? So we'll just put the final temperature. And here we now can determine the volume of the vapor to be equal the total volume total, right, subtracted the volume of the liquid, which we determined earlier. So right, so the next equation is we can use our pressure, so the partial pressure of air. So as we don't know anything about the air, we can assume that it's an ideal gas. So we use ideal gas equation to determine its partial pressure. So N air divided by R multiplied by the final divided by the volume of the vapor, right? So then if we go down, we can see here the partial total pressure of the system is equal to the partial pressure of the air, so plus the partial pressure of the water, which we defined earlier here. And the next equation we can use is here. This is the amount of the water in vapor state, vapor, right? Would also be assumed to be an ideal gas. So it would have pressure of the water, which we defined earlier, multiplied to the volume of the vapor. And we subtract that, we divide that by R multiplied by the temperature final, right? So now we have our basic equations that we that we can use actually while determining our function. So when we run this, and when we try to run our root solver, here says there is an error. MEB total is 1, so it can be the error. Root mass of the liquid is not defined, so let me check here. So we might have used two different things in two places, so that might be causing a problem. Okay. Oh, actually, we forgot to use one more equation here. So we know that mass of the liquid, here we can add one more equation here. So when we look at this equation for the total mass, we know that the mass of the water in liquid state would equal to the mass of the water total. So like mass of the water liquid would equal to the mass of the water total, right? Subtracted the mass of the water in vapor phase, which is the amount of the water in vapor state multiplied by the molecular mass of the water. So we have NV, amount of the water in vapor state, multiplied by 18, multiplied by the 10 raised to the power negative 3. Because we're using SI units, we have to determine the molecular mass in kilograms per mole. So when we just run it, so when we run this time, so it's saying vapor. So we might have two different equations again. So we should have used desired right here, as we already give the value for the desired variable. So here we go. When we run our program and run the root solver, we can actually get the final answer for our equation. So these values under the x, so this array would represent our value. So as you can see, this is the vector, and so as it is displaying the vector. So if we just unpack it, so total would equal to the root, the value under the x. So here, now we can get the values for final temperature and V total. So these would be our final answers for the question provided here. So in this video, we'll look through the question. So we'll look through the sample question. We'll look through the concept of it and determine which equations we can use. And then with the help of the SHE tools and the SciPy optimized root solver, we found the values for the final temperature and the total volume.